that you have your rational and irrational foldable completely colored and cut out, we're going to start with the top part, which is the rational definition. And I would like for you to write the rational numbers definition at the top of your foldable. A rational number is a number that can be written as A over B, which is a fraction, and A and B have to be integers, but B cannot equal to 0. And we're about to ask Siri why that is, so that you can remember why 0 cannot be in the denominator. Now we can remember that if 0 is in the denominator, it is undefined, and Siri will always remind us of that. So now I want you to go to the bottom section, or the middle section of your foldable. And on one side, I want you to split the foldable in half. On one side, you're going to do the rational examples. On the other side, you're going to do the irrational examples. So please make your rational examples list. The first example is a fraction, because by definition, a rational number is a fraction, unless 0 is in the denominator. Then we have whole numbers, integers. Those are the positive and negative numbers on a number line. The ones you put on a number line when you make one. Terminating decimals are decimals that stop. They have an ending. They don't keep going on. They have an actual ending. A repeating decimal is one that goes repeating on and on and on and never stops, but there's something special about it. It's going to have a repeating bar over the decimal that's going to repeat. Then you have perfect squares. Those are numbers multiplied by themselves 2 times, and you have a table for that. And the perfect cubes. These are numbers that are multiplied by themselves 3 times, and you have a table for that as well. Now let's fill in the second half of your middle section and do actually we're going to fill in the bottom part and do the definition of irrational numbers. So irrational numbers are numbers that cannot be written as a fraction. They can only be written as non-terminating and non-repeating decimals. So let's go to our list in the middle now. And these are the only irrational examples that you're going to write. The examples for irrational are non-terminating, non-repeating. That means it goes on forever and it doesn't repeat. You also have the non-perfect squares. Those are ones that are not going to show up on your squares table. You would have to actually do estimating on them. And then you have the non-perfect cubes. And finally, pi, which is an example of a non-terminating, non-repeating decimal because it goes on forever and it does not repeat. And here is the symbol. Now you can go ahead and glue in your foldable, and we're going to start the examples that are going to go below it. Here are the directions. Determine if the number is rational or irrational. Explain your answer. Example 1 is the number 6. So what we're going to do for each of these problems is determine if it's rational or irrational and say why. And the why is going to come from the examples on your foldable. The number 6 is a whole number. It's also an integer, but both of those are going to be on the rational section anyways. So this statement is rational because it is a whole number. And I would like for you to highlight or underline the word whole number. So you see these are examples that you got from your foldable. Number 2, 4/9. 4/9 is a fraction, therefore it is rational. So our statement, rational because it is a fraction. Number 3, negative 116. And I just told you that it is rational, but you have to tell us why. Of course, it is rational because it is an integer. And again, underline what I have underlined in your notes so that those stand out as examples from your foldable. Here is example 4, the square root of 5. So the square root of 5 is irrational because it is not a perfect square. So irrational because it is a non-perfect square. Question 5. Negative 12 and 75/100. This is a decimal that ends with the number 5. So it is rational because it is a terminating decimal. Number 6, the square root of 16. Because the square root of 16 does equal 4, it is a perfect square. So it is rational because it is a perfect square. Number 7, 5.36 with the repeating bar. Because it has the repeating bar, you know that the 3/6 repeats. Therefore, it is a repeating decimal. Because of that, it is rational. So we would write rational because it is a repeating decimal. Number 8, negative 35.9853 ... Because you have the ... you know it's a non-terminating, but then we have to see if it is repeating. Because it is not repeating, we do not see a pattern. We know that it is going to be irrational because it is a non-terminating, non-repeating decimal. Number 9, the cube root of 8. Because this is a perfect cube, the answer equals 2, you know that it is rational because it is a perfect cube. Our last example is number 10. 6.3434 ... Because you can see that it is non-terminating, you have to look to see if there's a pattern. The 3434 does show that there's a pattern, so even though there's not a repeating bar, this is a repeating decimal. So it is rational because it is a repeating decimal.